Okay, today we are going to talk about density, the density of objects. So we all know that there are three common phases of matter, and those are solid, liquid, and gas. A solid has definite shape and size. An example of a solid is a rock. A liquid has definite volume, but takes the shape of a container that it's in. So an example of a liquid is hot tea. It will take the shape of whatever cup that it's in, or mug or teapot, but you can never change the volume. And a gas can take any shape and easily be compressed or expanded, so its volume varies depending on pressure and temperature. It turns out that liquids and gases both flow, so they belong in a category called fluids. And that's what we're going to be talking about. There are two other phases of matter that don't get as much attention. And the first one is plasma. And plasma is like a gas, but it's a collection of charged particles. And this usually happens at really, really high temperatures. And it turns out, we don't talk about it a whole lot, but it's super common. Flames, lightning, stars, and even empty space are all examples of plasma, a group of charged particles. The other one is called the Bose-Einstein condensate, and it's really bizarre and it's really rare. In the Bose-Einstein condensate, there are a lot of bosons, and they collapse into their lowest quantum state. So that means that quantum effects can be observed, which is really, really strange. So what happens is if you take a solid and you cool it down near absolute zero, things start acting really funky. And this leads to something called superfluids. And superfluids do really bizarre things. They seem to not obey the laws of gravity at all, and they just act really, really strange. And this rarely happens. You have to get matter really close to absolute zero for this to happen. So density. In physics, we represent density with this little symbol. It's like a squiggly P, and this is the Greek letter rho. Anytime you see a squiggly P like that, it's rho and it means density. And hopefully from chemistry, you all remember that the density of an object can be calculated by dividing mass by volume. In physics, we are going to measure density in kilograms per cubic meter. So if you think about it, a cubic meter is really, really large. Take a meter stick and lay it down, and then another one next to that at a 90-degree angle, and then another one up in the air, and that's a cubic meter. It's gigantic. So just keep that in mind when you're thinking about the number that you have for the densities of certain objects. And an important one to remember is that water at 4 degrees Celsius has a density of 1,000 kilograms per cubic meter. So if we had a cubic meter of water, it would weigh 1,000 kilograms. We're going to use this number a lot, so make sure you file that away somewhere. But not everything has the same density, obviously. If I take a chunk of lead and I compare that to the same size piece of paper with the same volume that I crumpled up, those densities are going to be very, very different. So these are some common densities. We know that water has a density of 1,000 kilograms per cubic meter. And gold is much more dense than water. If we had a cubic meter of gold, it would have a mass of 19,300 kilograms. Something that's really interesting is that when water freezes and becomes ice, it becomes less dense. Which is very strange, because when most objects go from a liquid to a solid, they become more dense. Ice is weird in this way. Seawater has a slightly different density than regular old distilled water, and that's because of the salt content. And gases also have densities. So air has a density of 1.29 kilograms per cubic meter, which seems strange, but air is made out of particles, and particles have mass, so if we collect enough of those particles, we will be able to detect the mass. So if we have a cubic meter of air, it will weigh over 1 kilogram. So let's do an example of how you would use all this information. In the movie The Italian Job, the trunk of a Mini Cooper is filled with gold. Assume the dimensions of the trunk are 0.85 meters wide by 0.55 meters high by 0.33 meters deep, and it's completely filled with gold bricks. How much mass and additional weight does this add to the car? So, remember our equation, rho equals mass divided by volume. So, the first thing we need to do is figure out the volume of this trunk. So, this is a geometry problem. Length times width times height will give us volume. So the volume of this trunk is 0.154 cubic meters. So now we know volume. We also know the density. We know the density of gold is 19,300 kilograms per cubic meter. So if we want to solve for the mass, we use our equation over here, and we plug in for volume and density, and we solve for mass. And when you do that, it turns out that a mass of this much gold is going to be 2,980 kilograms. That's pretty hefty. So we know how much mass is added to the car. It's 2,980 kilograms. But this question's also asking us how much weight does this add to the car. So, to find out the weight of an object, we multiply its mass by the acceleration due to gravity. So we take 2,980 and multiply by 9.8, and it turns out that this gold would add over 29,000 newtons of weight to this Mini Cooper. And as a side note, the mass of a Mini Cooper is only a little over 1,000 kilograms anyway. So this is adding quite a bit of heft. So now, for your homework, you have two questions. The first one, a piece of wood that measures 3 centimeters by 6 centimeters by 4 centimeters has a mass of 80 grams. What is the density of the wood? And remember, our units for density are kilograms per cubic meter. Keep that in mind. Number 2, a cup of gold-colored metal beads. A cup of gold-colored metal beads was measured to have a mass of 425 grams. By water displacement, meaning we poured them into a cup and we saw the volume, how much that changed, the volume of the beads was calculated to be 48 cubic centimeters. Given the following densities, identify the metal. So I want you to tell me, is this gold-colored metal actually gold, or is it copper or bronze? You may need to use your chart back here to answer these questions and have them ready to hand in the next time you come to class.